Let's now look with more detail to the measures of spread. And here you are going to learn something new. Not this you already learned in previous years. The range, again, is the difference between the largest and the lowest value in a data set. What is the problem with this measure of spread? One of them is that it's very sensible to outliers. Imagine that you have, for example, 1,000 data sets, and they are all, or 99.9% of them are within the 400 and the 500 range. If eventually you have one value alone that is around, I don't know, 2 or 3, the range is going to be between that value, 2 or 3, and the 500 is going to be a wide range, although 99.9% of the data sets are within the 400 and the 500. Do you know what I mean? So it's very sensible to outliers. It changes automatically a sudden outlier being present there. On the other hand, it only uses 2 values out of the total number of data sets that you have, regardless what this number is the smallest and the biggest. It doesn't have any consideration about all the other values that you have there. So for most situations, the range is not a good measure of spread, so we need something new. Presenting the variance. Let me just go over what it is. The average of the square deviation between the data point and the data set's mean. Basically, mathematically speaking, this is what it means. If you look at this, you look at this explanation, and probably you don't understand it. Although you can actually solve all questions regarding statistics just by applying this formula. But I want you to have a visceral understanding of what the variance is. So I want you to look at this, focusing on what you have over here. What is this? X minus X bar. X bar is the mean, and X is an individual data set. So X minus X bar is a deviation of a data item from the mean. It can be a positive or a negative value. The mean lies, as the name suggests, right in the middle of the values, is the average of the values. So if an individual value is bigger than the mean, this is going to be a positive number. If an individual value is smaller than the mean, then this is going to be a negative number. What happens if you start adding, without the square, if you start adding all these deviations? I think it's logic to assume, and actually this is true, the sum of all deviations will be 0. The sum of all positive deviations, in other words, is going to be equal to the sum of all negative deviations. Putting everything together, this would be 0. So for every single sum of deviations that you would do, regardless of what you are measuring, this would always be 0. So obviously 0 is not a very interesting number because you cannot do anything with it. You need something different. That's why we square it, because every time you square a negative number, it will become positive. And now you may keep adding without the risk of the result to be 0. Actually, it will only be 0 if the mean and all the values from which you got the mean, they are the same. In other words, it will only be 0 if all the values are all the same. So what is the variance? The variance basically is the average of all the sum of these deviations. That's what you have over here. Squaring the deviation ensures that all values are positive. The sum of the deviations squared is represented by this. And if you divide it by n, this is the mean of all the squared deviations. And if you pay attention, the units are squared. So whatever this is, maybe centimeters, if we're talking about the length of something, the units of this is going to be centimeters squared. So is inconsistent with the raw data. If the raw data is in centimeters, the variance is going to be in centimeters square, so you have an inconsistency there. To fix this inconsistency, we have now the standard deviation, and this is the most important value that you are going to work with. What is the standard deviation? It's just the square root of this. Because if the units are squared, if you square root that, you have the units the same as the raw data. That's why we use the standard deviation more than the variance. Okay? The variance gives you a measure of spread, but so does the standard deviation. The smaller the standard deviation, the more packed together the raw data is. All right? So it's just the square root of the variance. It's the square root of that. In MF19, in the formula sheet, you will see this as this. Okay? How this is this mathematically goes beyond the scope of the syllabus. You just take it for granted. So you can get a standard deviation by the sum of all individual items squared divided by the total number of items that you have minus the mean squared. Everything inside the square root, calculator, and you have the standard deviation. It's important that you understand. You can apply just this without understanding the formula, but I don't advise you to do that. I want you to understand what you have over here. Because you will understand what you have here also better. Because for a frequency table, when you have group data, this suffers a little transformation, so you can account for the frequency, and this is what you'll have. You mostly use this version of the standard deviation. So look at it. The only difference is that over here you have to multiply the frequency by the data item square. If not present in a table already, you just add to the columns that you have this information, the x times f, the x squared times f, etc. Everything that you need in order to fill or to provide the information required to get the standard deviation, you add to the table. On the exercises that we're going to solve after this, you are going to see how this works. If you have a frequency table just with the class boundaries and the frequency, for example, you can do yourself getting the mid value, which is going to be each one of these, and the product of the mid value by the frequency, which is going to be required to get the average in the first place, the mean in the first place, the mid value squared times the frequency, which is going to be required to get this value over here. You have that for each line, add them all together, and you have this part over here. And in a table, you can get all the required information to get both the mean and the standard deviation. Very important over here, as a rule of thumb, if a value is 2 standard deviations from the mean, it should be investigated as it may be an outlier. How do you know if a value is an outlier? Measure the deviation of that value to the mean. If it is bigger than 2 standard deviations, obviously you need to calculate the standard deviation first. But if it is bigger than 2 standard deviations, either in the positive direction or the negative direction, it shouldn't be investigated as it may be an outlier. It is for sure an extraordinary value.